So welcome back guys. This is our problem number 12. So our supports have reactions. They are pin supports, but we won't be needing them because look at segment D to E. It is very hard to compute, to solve for the members by using the method of joints. So instead, we will use the method of sections. The method of sections is better and easier to use when we are pinpointing the members that we want. So, or just the part of a truss that we want to know the forces. Okay, I will draw the FBD through the segment A to A. I will skip the video. So we are done. So here we will take a moment at C because we can cancel out three forces that are affecting C. Now we can expose BD, and the slope is missing. So 60 multiplied to the 3, which is the moment arm, and we need to determine the slope with the 4/5 multiplied to the member BD and the moment arm. Do not forget the moment arm. So BD, let us check, let us type. We would have (75 kilonewtons). Look at the signs, we only have kilonewtons. So in cases where we have different forces or signs or unit for the forces, we need to convert them to a single unit, then we can calculate. Anyways, next is we will calculate the load, the unit strength, using the load that we have solved. So the unit strength of BD, segment BD, is equals to, we have a given of 1600 millimeter squared for every members. That means our cross section is constant throughout the truss. So take note that we have a kilonewton and we want to bring out, and our cross section is millimeter squared, so we need to convert it to newtons. So our answer is 46.875 megapascal. So there you have it. We have the unit strength for segment BD. Next, we need to calculate for CF. We can do it by taking a moment at D, cancelling the forces of segment CD and BD, and we would expose only 3 forces, in which 2 are already constant. So 90 times 4, the moment arm, plus 60 times 4 plus 3. Our positive direction is counterclockwise. So let us assume that CF is in tension, but it goes counterclockwise, so it will be on the other side. It must be compression. Anyways, slope is 4/square root 2. We can cancel the 4. CD is equals times the moment arm of 4 equals 0. So we can already notice that it is on the negative side. 1 over square root 2 multiplied to alpha x times the moment arm alpha equals 0 is negative. So 275.77 kilonewtons. So it is on the other direction, or in this case it is in compression. Remember, CF is in compression since we assume tension later. So next we can calculate for the unit strength of segment CF is load over area of CF. We have, just as I said earlier, our area is constant throughout the truss. It is multiplied millimeter squared multiplied to 10 raised to 3 newtons. We'll have newtons over millimeters, so we are in megapascals. So our answer is 172.36 megapascals. Our unit strength for member CF is 172.36 megapascal. So we can let's try to determine BC, segment BC. That means from the segment A to A, we cannot solve for BC because we did not expose the segment itself. That's why we cannot solve. That means we need to cut another segment. Let's name it BB, and I will skip the drawing part again, or the part where I will draw the FBD or free body diagram. So we can take a moment at D. Why at T, not at T? So I also draw the forces at CF and the 90, the segment CF and the 90, but we do not need those, but it will help the imagination. So we only have two forces, which is the BC and the 60 kilonewton, multiplying it to their respective moment arms. So next is to try it on the calculator. 60 times 7, so we have 105, negative 105. So again, since it is in the negative side, it means that it is on the other direction. Since we assume tension, it must be in compression. So next is we can calculate for the unit strength. So the load of BC, which we just calculated, over the area, which is uniform all throughout the truss, we would have 1600 on the area, millimeters squared. So let's type it. Raised to 3 over 116 is 65.625 megapascal. So our unit strength for the member BC is 65.63 megapascal. Comparing it to the other, so we will write them in summary. Is megapascal. The unit strength for CF is 172.36 megapascals, and for the unit strength of BC, we would have 65.63 megapascal. So let's write there. So that is compression. This is also compression. Lastly, segment BD is in tension. That is all, and I hope to see you in the next problem. So welcome back, guys, to our 13th problem. So first we have a slope in degrees here with respect to the degrees. So that is sine opposite, right? Sine 50 degrees, cosine 50 degrees. Now we need to expose again the forces on the cables. Now we know that a slope, when two slopes are perpendicular to each other, or two lines are perpendicular to each other, the slope of one line is the negative reciprocal of the other. So I will show you about it later. So this is the FBD. I will skip again. So this problem is the same as the uniform cylinder problem that we've had earlier. I believe that is problem number 10. So the joint T, the rigid bar at joint T is leaning on the 50-degree slope with respect to the horizontal. So since the slope and the force of the support are perpendicular to each other, we will have the dimensions or the rise over run of the slope as the other side. So our rise is cosine 50 and our run is sine 50. So taking summation of forces of x equals 0, going right is positive. We would have, so our first cable A to B is the same as our problem in our number 3 problem. So they are a single cable. So if you have missed that, you need to go back because I explained how that works. They are a single cable. Math is a subject that you cannot learn by skipping through steps. So let us solve for forces x. So here, let us write the component with respect to the x-axis. So it is on the reverse. So I forgot to switch. I placed the dimensions at the wrong sides. I'll correct it. So for slope 2, our rise is cosine 50. And in my drawing, it was sine 50. It was just the other way around. So let us flip. This should be sine, and this is our slope to right. Our rise should be cosine, and there's our run should be sine. Anyway, so we have two forces on the horizontal, right? Tension AB at joint B and tension C can be neglected because they are on the vertical. So let us name the force at D as R sub D, or the reaction at D or resultant at D. Let's name it R sub D, or since we name it RD, so we can calculate. So our value is 1.1305, of course, 1305. That is tension AB. So next, we need to summate forces at the vertical. So I will write the components. This should be sine 30, right? It is the opposite since it is with respect to the horizontal axis at joint A, and here at joint D, or at the resultant at D, or the effect of the incline 50 degrees to the joint D, we will write the components. So sum of forces Y, we have 1, 2, 3, 4. All the forces have Y components. So this is sine 30. Since it is the same cable at and with AB, we can just add 1 plus the tension at C that only separate. It is separated. Okay, we forgot to write the effect of the rigid bar, the weight. The effect of the weight, it is of course in newtons, and this is so rise, so cosine 50 multiplied to, so that is the rise of the slope to right, so multiplied to the reaction at T. So we can simplify, we can substitute RD or the reaction at T to make it 3 unknowns, right? We would have 3 unknowns. So next, we can use the calculator to simplify this. By the way, if you notice, most of our problems would have the same number of unknowns with the same number of cables of the forces, of the missing forces. I mean, in this case, it is cables. So we have 3 unknowns in this equation 1. So we can bring out tension of AB and AC by taking a moment at T. Right? We've already simplified. We've already listened the number of unknowns by our first 2 summations. We summate them at X and at Y, so we can cancel out the reaction at T. So, and then we can take a moment at T. We already know it's the worth of segment D with respect to the TAB, TC, and W. So bring out W, we would have 2 times TC, and just this is algebra. You can check. For plus sine 30 multiplied the moment arm. This is AB. Simplifying, we would have 4. Cannot see. 4 plus sine 30 multiplied to 6, that is 7 multiplied to R. Tension at AB, that is our equation 2. So we can simplify this by using elimination or substitution, but I will use by elimination. So it is better to use the one with the higher values on the upper side, so we will have positive, but you can use the other way around. The only problem is you will have a negative and you need to switch them again, and if they both have negatives on both sides, they would also be equals to positive. Anyways, let us times 2, so 2 times TC minus 2 TC of tension at C would have of course 0, and last is 2 times 2.2267, so 7 minus 2.26. So our answer would be 2.5466 of times tension at AB. So W, as you can see, we can already compute, right? I believe it. Yeah. So W, we can bring out the AB, which is also, of course, which is the load, our load, of course, will W, that is simple algebra, 1 over 2.5466. Since we are trying to determine the weight, we can already solve, because we already know the ratio of the load to our weight of the TAB to the weight, right? That is why it is 1 over, so one weight is 2.5466 of TAB. That's why it is a ratio. If we try to think of it in another way, one weight is equals to 2.5466 TAB, tension at AB. That is the relationship. Anyways, weight is equals to, has a unit of newtons, and mass is kilograms, and gravity is meters per second squared. So our equals 0.3927. We have 63,775. 51. What is this? Newtons. Now we can calculate the mass by dividing the load, the weight, by the gravity, 81. So we would have, so let us double check first. 63.661 is 63.661. I believe I had that typo. So yun lang yung nagkamali natin. So answer 9.81, 6489. In the way, our reference book is called Strength of Materials by Mathalino.com or Mathalino. So converting this, putting the kilogram to megagrams, would have, of course, let me show you. If you 49 megagrams. So I double checked using the calculator. Anyways, for our cable AC, we have the same, right? Let us use the relationship that we had computed earlier. So from equation 1, we have weight is equals to 2.226 tension of AB multiplied to tension of AB plus tension of AC. Now we have AB, so I think I made so that should be A. It was the one below, but it's the same. We can transpose. It's the same. Is minus W. So we just exchanged. Our signs are wrong. That should be positive and it should be negative. So plus multiply to 0.327. Our value is 0.125 6 of W. So our ratio, the ratio of our tension AC with W is 0.1256. That means tension AC is very strong. Looking at the numbers, if you comparing it to the ratio of our other cable with the weight limit type, space, see, we have a unit, it is capable of carrying of taking in the load of 238,853.5 newtons, while comparing to the AB, the capabilities of AB, it has 63.661, meaning we cannot exceed the limitations of tension AB. That is why we can locate the heaviest mass the bar that can be supported at AB, segment AB. So thank you.